Hello. In today's lecture, we're going to be going through tutorial 7, which is on the simple pendulum. Okay, so we won't be going through all the answers, but just a rough idea of what you need to do for the tutorial. Okay, so before we get into the questions, let's just do a quick recap on how we get the equations of motion from the diagram of the simple pendulum. So usually we draw something like this, where we've got some sort of ceiling, then our pendulum with the bob of mass m, the rope of length L, making some angle theta with the vertical. Okay, so we did this before, going through the forces involved, but let's just go through that again. So we've got Fg going down, so that can be written as m times g for gravity. Then we have a tension force acting through the rope. Okay, so those are the two forces. However, we would like to find not the forces in the usual xy, like this. Okay, that's not going to be so helpful because we've got the circular motion. So choosing coordinate system like this, the typical Cartesian, is not very helpful. So instead, we choose a coordinate system like this, okay, where we look at the rope forming our new quote-unquote vertical, and then we have the other direction perpendicular to that. So we say that this is our radial direction, okay, because it's going radial from the point of contact with the ceiling. And then we have our angular direction that will either increase or decrease our theta value. Okay, so that's just how we need to view this. Okay, so let's just get rid of that. Okay, so if we stick with that, we're going to have a force in the theta direction, and we're going to have another force going in the radial direction here. So we have tension moving upwards through the rope, and to counteract that, because the bob is moving with a fixed distance L from that contact point, there must be another force balancing out the tension. And that's going to be mg cos theta. Please refer to the previous video to see how we get this from the little bit of trig. Okay, and then the other one here is going to be minus mg sine theta. Okay, the minus is because we're moving in the minus theta direction. Because if we go from this current angle down to the vertical, theta gets smaller. Okay, so that angle gets smaller going there. And then if we move upwards towards the ceiling, theta gets bigger, so that's the positive theta direction. Okay, so we can write out our net force. That's going to be this one over here, because that's the force needed to move this mass along the arc. Okay, the tension and the mg cos theta, those are balanced, so that's that doesn't add anything to the equations of motion. Okay, so Newton's second law, F net equals ma. So we can write ma, but we would like to write a in terms of theta, but that's fine, because we know that the distance covered by the bob, let's call that, let's not call it d, let's just call it x, is equal to L theta. Okay, because theta is radians. So if we multiply that by the radius, we get the arc length. So in this case, x represents this arc length distance here. So that's x, that's L, and that's theta. Okay, so that's the arc length. Now we can just do double derivative on x to get the acceleration. X double dot is L theta double dot. Okay, so if we just have the angular velocity or the angular acceleration, we just multiply that by L and we get our linear one that we're interested in. Okay, corresponding to the tangential motion. So ml theta double dot is equal to minus mg sine theta. Okay, because that was our net force that we figured out from the diagram. Okay, a little bit of rearranging. We get theta double dot is typically rewrite it like this, plus G over L sine theta is equal to 0. And we usually make the definition, omega squared is equal to G over L. Okay, so omega is the angular velocity. Okay, theta double dot plus omega squared sine theta is equal to 0. Okay, now this is non-linear because we've got sine of theta. That's a non-linear function. So this is a non-linear second order differential equation. Okay, which means we can't use those standard methods we saw in the last chapter because those only worked for linear differential equations. Now, we could linearize this and then convert this into an approximate form, which is linear, and so we can solve it. But we're not going to do that here. Instead, we're going to use a program that can use the Euler method or the Runge-Kutta fourth order method to solve this computationally. Okay, because those can handle these nonlinear equations. Okay, so the way that we do that computationally is we introduce a new variable. In the tutorial, we see that it's called capital omega. So we introduce capital omega as theta dot. Okay, so that is our extra variable that we include to turn this single second order differential equation into two first order differential equations. So if we include this here, we end up with capital omega dot is going to be minus omega squared sine theta, or we can imagine this as some function f of theta, omega, and t. Yeah. Now, this capital omega doesn't appear on the right-hand side, but we can still imagine that as a function like we described with f there. Okay, and then we can have theta dot is equal to, again, capital omega, and we can imagine this as g of theta, omega, and t. Yeah, so the way that we do that is because we want to imagine these as two first-order differential equations that we can then solve with the Runge-Kutta method. Okay, so the tutorial says use the Runge-Kutta fourth-order method. Yeah, so we solve these using the Runge-Kutta method for each one. So you would use the Runge-Kutta, finding the k values and then implementing that updating procedure for both equation 1 and equation 2. Okay, so we do it simultaneously. So solve these two using Runge-Kutta fourth order method. Yeah. And then in the tutorial, it says that we have some initial conditions. Theta at 0 is pi over 4. And omega at 0, so that's our initial velocity. That's going to be 0. Okay. So that is questions 1 and 2. Okay, then for question 3 on energy conservation, what we need to do is find the kinetic energy and the potential energy as functions of time. Okay, so energy conservation. Okay, so how do we write the kinetic energy and the potential energy of this particular system? Okay, so the kinetic energy is quite simple. It's just half mv squared. remember that V is given here. So X dot, in this case, will be L theta dot. But then if we want V squared, we need to square both sides. Yeah. And then the potential energy, that's just given by the height of this mass over here. Okay, so it will be L cos theta will give us the vertical height, and we need to put a minus sign. Okay, so I'll let you think about why we need to put a minus sign in front of that potential. Okay, think about how the potential energy changes when things move up or down. So think about that in terms of this angle theta and this so L cos theta being the height. Okay, so why do we need a minus sign there? Okay, so the kinetic energy, K, is going to be half mv squared, or as we put it here, x dot squared. So it will be L squared theta dot squared. So it will be half m L squared theta dot squared. But we don't know theta dots. Remember here we said theta dot was capital omega. So we can put that in. Half ml squared capital omega squared. Okay, so as we are updating using that Runge-Kutta method, we're going to be collecting the values of omega and theta. Okay, so we always keep those in a list. Once we have those in a list, we can then do these calculations here. Okay, so if we have a list of omega values over time, then we can calculate the kinetic energy over time. Similarly, with the potential energy, let's call it U. That's going to be minus mg cos theta. And we know the theta values from here. So equation 2, if we solve that, we get our theta values. Once we have the theta values over time, we can calculate the potential energy. Yeah, and then we need to plot the two of them over time. So then we have T, and then our energy E, and then we can write the energy in terms of its two parts. So remember, E is equal to K plus U. So it's going to end up being some sort of sinusoidal kind of graph. Yeah, so it'll be something like this. Yeah, where we've got the potential energy and the kinetic energy. And if we add the two, we get the total energy. But as time goes on, the kinetic energy will go up because the mass starts moving, and the potential energy goes down because it's getting closer to the bottom of the arc where it has lowest energy. And then once it's at the bottom of the arc, it's going to be at this point here. It then overshoots the bottom. Then the potential energy goes up again, and the kinetic energy, potential energy goes up, and the kinetic energy goes down until it slows down at the maximum angle on the other side, and then the process continues. So we end up with this sinusoidal behavior. Okay. Then that was question 3, and then question 4 was the theoretical solution. That was where I was speaking about linearizing those equations. So if we go back to the equations of motion over here, okay, the sine theta term is non-linear. However, for small values of theta, we can approximate it as linear. So let's just go through that. So linearized approximation. Okay, so if we imagine the sine theta function, looks something like that. So this is theta and sine theta. If we look close at theta equals 0, let's get a different color. We see that this function is well approximated by a straight line. We can see that if we find the Taylor series of sine theta. So find Taylor series of sine theta and only take the linear terms. And only take up to linear term. Okay, so we have the constant term and the linear term. That gives us the straight line. So if we expand this out in a Taylor series and only take those first few terms, so not the quadratic and onwards, then we get a linearized approximation. In this case, if you do the Taylor series expansion, we see that this is approximately theta. So there's no constant term because it goes through the origin. So there's no vertical shifting involved. Okay, so if we do that, then the equations of motion become theta double dot plus omega squared theta is equal to 0. Okay, so here we use sine theta is approximately theta. Now that this is linear, we can then solve it. Okay, so we can either use the methods of differential equations that we did in the previous chapter, or you can use that exponential method that we looked at last time. So remember, the methods of differential equations only gave us the theta function, okay? Whereas the exponential method gave us theta and theta dot. Okay, so you do a bit more work, but then you get both the angle and the angular velocity, okay, which we will need for this energy conservation question, because we see we've got this omega and we've got this theta. Okay, so it would be better to get both of those at the same time. Okay, but that's up to you, unless it is specified in the test. Okay, so just read the question carefully to see if you're free to use whatever method you like, or if you need to use a particular method. Okay, but we've gone through this equation many times. You can go ahead and solve that for yourself. Okay, so that is it for tutorial 7. Remember that this is due on Friday. We will go through it again on the Wednesday, but please give it a go before then. Okay, if you have any questions, please don't hesitate to email me.